So here are some typical workloads that need big compute. Digital renderings. We actually have been working with Pixar and a company called Green Buttons. So they have been rendering real movies that are actually going to be published using Windows Azure. So digital media rendering, and it's also very much embarrassingly parallel, which I would explain later. What it means is that every single unit of work is very well encapsulated, meaning that perhaps each frame of these movies are rendered independent of all the other frames, meaning that the work can be easily parallelized out and be able to utilize many cores in parallel. So financial and insurance risk calculation. This is also one of those scenarios that are widely used. And in fact, we have a demo later today using SignalR and also the HPC scheduler to get some real-time calculation for risk management. And then engineering, modeling, and simulation. So this is the traditional compute. So they generally tend to use these linear algebra libraries to model a physical system. So for example, so there's a lot of CFD simulations or computational fluid dynamics simulations that are used by car manufacturers to make sure that their car models are efficient. So those type of applications tend to require very fast interconnect, which our new HPC SKU in Windows Azure will be able to provide with 120 gigabytes RAM and 16 cores and some of the best processor that's in the industry. And also computational life science, probably one of the most scalable type of applications. So I just talked to folks at the NCSA. They have a new machine called I think it's called Blue Water. That machine has 370,000 cores. So they are able to use the entire 370,000 cores running one simulation. So namely a computational code called NAMD for molecular dynamics computation. And then Earth and Science. Earth and Science are also very important. I actually have a weather simulation as a portal to show you at the end of this presentation. And also data analytics. Data analytics involves Hadoop and other interesting big data computation. So I like to think of big data being part of big compute. It's a subset of big compute, where instead of using lots of CPUs, you end up using the hard drives on your machine. So for example, Yahoo tends to have these really large Hadoop clusters, which have 24 disks per spindle per node. So instead of emphasizing on processor power, they emphasize on I/O-intensive applications. I will probably be doing a big data presentation in the coming months. But for this particular presentation, we'll focus on only big compute, which is only CPU compute intensive type of workload. So here is an illustration of something called an embarrassingly parallel application, which works great on cloud and, especially in the cloud, on large clusters, and especially on the cloud, because each unit of your work is not dependent of each other, meaning that you can spin up as many processes as you like. So we mentioned a few of those type of applications. Digital rendering is one of the largest, and also insurance computation. So people could be computing different portfolios on each of the processes independently. There's, as you can see, there's absolutely no communication or very little communication between all the different application logics that runs on each of the compute nodes. And here's a very interesting example. This is actually an engineering application, but on the other hand, what these guys are doing, it's a company called Design Optimal Solutions. So what they're doing here is doing design optimization. So they're simply varying the parameter on that elbow-looking device, which is actually an exhaust pipe. They're trying to maximize the efficiency of this device by varying the geometry of this device. So by changing the mesh a little bit and be able to come up with let's just say 5,000 slightly varying variations for the design, they are able to save 3%. They are able to achieve a 3% efficiency improvement. And I think it took them maybe 60 engineers at Ford to be able to do the same. But unfortunately, they were the human beings were only able to do about 0.6%. So this is a very typical workload that people run, which is to change the design slightly and go ahead and run variations of the same design and look at the end results to see which configuration works the best. And each of these problems are relatively small, but you run thousands and thousands of them to come up with an optimal solution. So here's another example. This is also an engineering application. There's something called MPI. It's been around for, I would say, 30 or 40 years. And many of the senior leadership at Microsoft, originally, many of them from Microsoft Research, invented this protocol. And folks like Tony Hay have actually written the spec or proposed specs of this many, many years ago. So these type of applications are essentially solving these large linear systems or matrices. So nowadays, you probably wouldn't write anything using MPI. You're probably using a numerical library that sits on top of MPI to be able to do the computation. So these type of applications require specialized hardware. This is where these large clusters at national labs tend to be able to afford, which is extremely large, good interconnect. Here's actually a simulation that we ran, and it's simply showing you the precipitation. Actually, it's a weather application that I ran, and it's showing you the precipitation over a year around the country. As you can see, it does rain a lot in Seattle, and especially in Seattle area, it just rains a lot. So that's why I have moved out of Seattle, and I have I'm now actually based in Boulder, Colorado, which is a lot drier and has a lot more sunshine. But just don't tell that to my colleagues. So here are the some of the new hardware that's coming up. One of them is a 8-core configuration with 60 gigabyte, and the other one is 16 cores with 120 gigabyte instances. So all of these are actually virtualized. That's actually the amazing work that Microsoft's server team has done. So this is the RDMA work they have done to do the virtualization, meaning that the interconnect as well as the CPU are extremely efficient, even though they are virtualized. I've actually done some performance tests on them, and the most recent LIMPAC run they've had is actually running at 90% efficiency, which is considered very good without virtualization. So with virtualization, we're able to achieve extremely good performance on these hardware virtualized. So the point is that there's a lot of work that has been put into this, and it will be really fantastic for any type of scientific engineering applications to be able to run on our cluster, the new hardware, when it becomes available. And we are going to have, probably pre-release coming up in the next 3 or 4 months. So if you have any questions, please do feel free to type them in, and I'll answer all of them at the end of the session. The third type of applications, we went through something called embarrassingly parallel application, which it's the simplest thing to run. In fact, a lot of cloud compute hours are run using that. So there's no communication in between. And then the second type of application, which is very tightly coupled, meaning MPI type of application, are the traditional HPC applications. So those applications tend to use a lot of CPU, and they tend to chat a lot. So you need these very expensive interconnects to be able to run those. And the third type is becoming even more popular these days. It's called the IO-intensive application. So mostly people are aware of this through something called big data. So Hadoop runs that way. So it's very similar to HPC applications where you're clustering a large amount of machines together to be able to do the work. But in this case, you are maximizing on the I/O capabilities of these clusters, and you'll probably use a relatively simple paradigm called MapReduce to be able to run your application, meaning that you would actually take your code and map them onto the nodes that actually have the data on them. So it's a distributed system with a distributed file system for you to be able to run data-intensive applications. So we're not going to discuss that so much today, but I'll probably have a session in the coming months to discuss Hadoop and Microsoft.